welcome to on digital signal processing. In this class, let us look at the possibility of reconstructing a time domain signal from the samples of its frequency domain representation. What I mean to say is that a signal x of n, which will be represented in time domain, can be represented as x of omega in the frequency domain. This representation, that is from time domain to frequency domain or vice versa, which is indicated using this double arrows over here, is assisted by the Fourier transforms or Fourier series, right? So you have come across these concepts. Now, is it possible to take a few samples of x of omega and obtain the x of n back, is the topic for today's discussion. But what type of x of n are we going to consider? The x of n, that is the time domain signal, this will be a discrete time signal. So we are going to consider only the discrete time signal in this set of discussions. Apart from discrete time, these signals are also energy signals. So they are going to have a small bursts, you can say for example this kind of signal. Okay. So it is say defined over 0, 1, 2, 3, 4, 5, 6 up to say 10 example, and beyond that the samples die, or even before that also the signal is 0. So this kind of signal, it can be even represented in the form of a sequence, for example 5, 4, 5, 3, 6, 2. The origin can also be shown with the help of a simple arrow mark over there. So these are the type of signals that we will see in the discussions on digital signal processing. Now these signals are going to be represented using the Fourier transform. What is the Fourier transform of x of omega? So x of omega, which is the Fourier transform of the signal x of n, is represented as summation x of n e raised to minus j omega n, and this range of n we will consider it as minus infinity to plus infinity. This is the representation of the signal. But look at what type of x of omega will it be. X of omega will be periodic in nature. This is the nature of Fourier transform. You can go back to the discussions on Fourier transform to get an insight about the type of representation in the time domain and the corresponding types in the frequency domain. So just as a hint, if the signal is say aperiodic in one domain, it will be periodic in the other domain. So this signal, which is x of omega, is aperiodic. Obviously it is a energy signal. So this representation in the frequency domain will be periodic. Apart from periodicity, this x of omega also has continuity, that is, it is a continuous representation. So both of this give us a wide opportunity to use for our benefit. Now first thing, let us look at this representation, that is how this x of omega would look like in the frequency domain. I am just assuming a signal like this, right? So this is continuous, this is one period, you can say, okay, 0 to 2 pi, and 0 to 4 pi will also be a similar signal, and before that also it will be a similar signal, say from minus 2 pi and so on. So this is suppose magnitude of this x of omega. Now one problem with these kind of representations is that since this is continuous, it is impossible to represent it using all the samples in a system, in a computer system. Why computer system? Because all these operations on the signal will be done by the computer. So I want to represent this signal in a computer, and if I have to represent, because of the finite memory availability in the computer, I cannot represent the infinite number of samples between 0 to 2 pi. This 0 to 2 pi range that is there, whatever information that is there is repeating from 2 pi to 4 pi and from 4 pi to 6 pi and so on. So what can be done? One better way is to restrict our uh, concentration only on one period or one cycle of this x of omega. And what is x of omega? You can recall x of omega is the frequency domain representation of our x of n. X of n is a discrete time energy signal. Examples are given here. Say first example or the second example you can look into. Now what we will do is we will neglect the x of omega from 2 pi onwards or before 0 and just concentrate on this range, that is from 0 to 2 pi only. So in this range we will try to look at the signal and take some samples over this range. Okay. Now how do we take samples? So what we can do is this entire 2 pi range that is there can be divided into say n equidistant strips, right. For example, this is first part, this is second part, this is third part, this is fourth part, fifth part, sixth part, seventh part and so on. This n can be any positive integer. Suppose I have 10 equidistant samples, 10 equidistant strips, okay. So you can consider any one strip into this, right. So I can say this is k equal to 0, k equal to 1, k equal to 2, k equal to 3. And what is this k? K is indicating the index. K is like an index for that particular strip. So the idea that is emerging out of it is that though there are infinite samples in x of omega, magnitude of this x of omega from 0 to 2 pi in this curve that you can see, instead of taking that entire infinite number of samples, I am now confining to a set of n samples only, number of samples, n samples only, and that sample is indicated using k. So k indicates the kth sample. For example, first sample, third sample, 25th sample, 50th sample and so on. So this k and 2 pi by n can further be represented instead of say x of omega as x of 2 pi by n and k. So this 2 pi by n k becomes one of our representation for only these samples. So this representation can be included in our previous representation, that is a previous equation over here. So the equation is summation x of n e raised to minus j omega n. So now I will write the expression as x of 2 pi by n k as summation x of n e raised to minus j, all things are as it is, except that this omega will now be replaced as 2 pi by n k into n. And again this range of n is from minus infinity to plus infinity. So the summation that you are seeing over here, that is x of k, that is there from minus infinity to plus infinity, how many samples are there? Obviously there are infinite number of terms over here. Now is it possible that each of this this particular summation can be divided into further infinite number of summations, but the condition is that each of this summation will have n samples. For example, assume that say n is say 100. So instead of having one summation from minus infinity till plus infinity, I will have multiple summations which will have, each of them will have say 100 samples. Okay, one summation here, one summation, one more summation, one more summation, one more summation, like this, right? This continues such that each of them have 100 terms in their summation, right? So this 100, if I were to replace it using say this capital N, then I will have say each term will have the same x of n e raised to minus j 2 pi by n k n, such that the n starts say from minus n till minus 1. After that the terms are all same, but next value after minus 1. So minus 1 is included here, after minus 1 it is 0. So from 0 this should have n terms, so n minus 1. And again the same term x of n and e raised to minus j 2 pi by n k n, and this goes on and on. Now, what is the purpose of doing this kind of representation? So that will be very much evident in the upcoming discussion. Now, since there are infinite number of such summation, how many summations are there? You know, each of these summations are having n samples, and such n infinite n summations will be there. So we will try to represent this using one more representation, one more convenient representation, that I will write it as x of 2 pi by n k, right? X of 2 pi by n k is equal to summation of summation. What are the terms? That is x of n e raised to minus j 2 pi by n k n. So this term is not changing. Only thing is, I will have the n ranging from say Ln to Ln plus n minus 1, where L ranges from minus infinity to plus infinity. Okay. So how is this being obtained? So we obtained this by extending, you can substitute say for example L is equal to 0. When you substitute L is equal to 0, what do you get? So when you substitute L equal to 0, the lower range over here becomes 0 into n, which is 0, and the upper range of this summation becomes 0 into n, which is 0, plus n minus 1. So the summation, one of the summation was of the same range. So summation n equal to 0 to n minus 1. So the summation of summation kind of representation can be obtained over here. Now the inner summation is having the index say L. So this inner summation index is n. If you were to change it to say n minus Ln, That means, the term over here can be taken on the other side. What happens is a very simple and very interesting phenomena. That is, x of 2 pi by n k is equal to, and also we are going to change this order of summation. So if you bring it on the other side, this will become n minus ln. So I can write it as n equal to 0 to n minus 1, and the summation has been wherever we had n, so you can replace it by n minus ln. So we had x of n, that becomes n minus ln, correct, and we get e raised to minus j 2 pi by n k. You can also observe there is one more n here, so that also I shall replace it as n minus ln. Okay, and this inner summation will be L is equal to minus infinity to plus infinity. This is the change. Now keenly you can also observe that this particular representation over here has a term which when expanded gives you e raised to minus j 2 pi by n k into L n is there, right. So you can cancel that minus and minus. So what happens is this and n both in the numerator and denominator get cancelled, and we get e raised to j 2 pi L and k. So both of them are integers, and the integer product of 2 pi is again 2 pi. So you will get this whole thing equal to 1, because it is going to be some cos of 2 pi kl plus j sine 2 pi kl. So we will end up with this term being 1. So this whole representation can be reduced to summation n equal to 0 to n minus 1. This first thing, summation x of n minus l n, L equal to minus infinity to plus infinity, e raised to minus j 2 pi by n k into n. Okay. What happened to the term minus ln? So that part is explained over here. So that becomes equal to 1. So that becomes equal to 1. So that can be neglected from the expression. So this expression is of utmost importance for us now, because what it is telling is that we are having on the left hand side, you can see it is the samples of the x of omega. This is nothing but samples of x of omega. So x of omega is a continuous entity, and this samples are there, and these samples are, how many samples are there? So we have capital N number of samples are there, and this k indicates that kth element. So it can be say 5th or 6th or 7th or 20th or 500th and so on. So this is x of omega, samples of x of omega on the left hand side. But one interesting thing has happened on the right hand side. So I want you to pay attention to this term in the bracket over here. So the term in the bracket is you can represent that term, right, as summation x of n minus ln, L equal to minus infinity to plus infinity, right. Can we call this signal as this whole portion as xp of n, xp of n. What is the purpose of calling it as xp of n? It will be evident shortly. What is the range of L? L is ranging from minus infinity to plus infinity. Can we take some examples of L and then see what happens? So if I were to expand this, say for example minus 2 to plus 2 range, if I were to expand, so it will be all dot 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 plus x of n. So for L is equal to minus 2, it will be minus of minus 2, it will be so 2n plus 2n plus x of n. For L is equal to minus 1, it will be plus n, okay. And for L equal to 0, from minus 2 to plus 2 I am looking at, from minus 2, so it should be x of n, right. On the same line it will be x of n minus n. Reason is for L is equal to 1, it will be 1 times n, and so on, plus x of n minus 2n, plus like that, it goes on and on. What is to be observed over here? You can observe that each term in this representation, that is x of n plus 2n plus x of n plus n, all these are basically x of n itself. But only thing is, the x of n is delayed by n, this term is delayed by 2n, one more term will be delayed by 3n, delayed by 4n, and so on. On the other side, you will see this term is advanced by n, this term is advanced by 2n, one more term over here advanced by 3n, advanced by 4n, advanced by 5n, and so on. That means it is the x of n which is repeating itself. So this is the periodic repetition of x of n. Now, why I am bringing up this point is that while discussing in the beginning, we said what is the type of x of n? X of n is a discrete time energy signal. So, energy signal means we also meant that it is a periodic signal. It is an aperiodic signal. So, this signal which is aperiodic is actually being treated as a periodic repetition of the aperiodic signal in the Fourier domain representation. So, this whole concept can be further taken in the terms of Fourier series. Reason is, the Fourier series can be applied when we actually have a periodic signal, that is a signal which periodically repeats itself, the pattern repeats itself. So, such signal is called periodic signal, it repeats, right. So, such signals can be analyzed with the help of a Fourier series. Now, it is possible, though we do not have that signal, but the rearrangement, it is giving rise to a representation like this, which is an aliased version or a periodic repetition of x of n. So, I can treat this expression with the help of a periodic, with the help of a tool which helps in analyzing periodic signals. That is nothing but our Fourier series, right. So, this Fourier series I can represent xp of n, right, which will be summation ck e raised to j 2 pi by n kn, right. So, k is equal to, we have how many samples? So, it will be n 0 to n minus 1, that is totally we have n samples. So, these yeah, of course, there is one more variable here, that is 0, that is n equal to 1, 2, 3, 4 up to n minus 1. So, this ck that you are observing here, this is the Fourier coefficient. So, we will be representing the xp of n in terms of the coefficients using this Fourier series representation. And how do you obtain this Fourier coefficient? So, Fourier coefficients ck can be obtained using this representation, that is 1 by n xp of n e raised to minus j 2 pi by n kn, okay. So, n is equal to 0 to n minus 1. So, this is our Fourier representation. Now the term on the right hand side over here, this is nothing but our Fourier transform. So I can write 1 by n into x of 2 pi by n k, 2 pi by n k. So for k is equal to again 0 to n minus 1. So Ck, which are the Fourier coefficients over here, can be obtained if the Fourier domain representation samples of the Fourier domain representation are available. So that is very clearly evident. So Ck can be obtained if you have Fourier domain representation, and if you have the Fourier coefficients, then you can obtain the time domain representation. So the idea that is being conveyed is that over here we can write it as xp of n. So I'll substitute this Ck back into this previous expression. So I will get it as xp of n is equal to, what is Ck? Ck happens to be summation this k equal to 0 to n minus 1. So I will replace this Ck using this expression, that is 1 by n into x of 2 pi by n k. The other part is as it is, that is 2 pi by n k n. Okay. So this is the representation. So on the left hand side you have time domain signal, and on the right hand side you have samples of the frequency domain representation. Okay. So from the samples of the frequency domain representation, the time domain signal can be obtained. So this is a very crucial concept in arriving at conclusion that the samples of Fourier domain representation or Fourier transform, samples of Fourier transform will help us in exactly reconstructing the original signal. Now you may have one question here. We on the left hand side have written xp of n, but what is the time domain signal that we considered? Is it xp of n or x of n? Our signal is actually x of n, right? So I have shown you here the representation that it is like periodic repetition of x of n, right? So if periodic repetition is given of x of n, is it possible to obtain only xp, if xp of n is given, is it possible to obtain only the x of n? Yeah, it is perfectly possible, because x of n is over here. Any delayed versions like x of n minus 1, x of 2n, n minus 2n, x of n minus 3n, x of n minus 4n, all those things are to be erased. And on the other side it is x of n plus n, which is advancement, x of n plus 2n, which is again advancement, all those parts are to be removed. So if you were to remove those or erase those parts, then you will get the time domain signal x of n from that. So the procedure to obtain x of n from frequency domain samples and hence the reconstructed version, that is xp of n, is xp of n for n in this range and 0 otherwise. Okay. So if x of n, an example I will take, if x of n is a signal like 2 to 4 minus 2, if this is the signal, how does periodic repetition would look like? So so the only signal, suppose this is origin, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10, 11 and so on. Minus 1, minus 2, minus 3, minus 4 on the other side. Suppose if I were to put this as n and minus n over here, how the signal can be represented? So this is 2, this is 2, this is 4, and this is minus 2 over here, right. This is x of n. And what is xp of n? Xp of n is the periodic repetition. So, the expression is x of n minus Ln, correct. L is ranging from minus infinity to plus infinity. So, it should be then delayed by 1 time unit, delayed by 2 time unit, and similarly this is advanced by n, advanced by 2n, and so on. So, this goes on, this goes on. So, the signal is defined only over the range, only over this range. So, if you want to recover this portion from the xp of n, so here only you find x of n, rest other things are xp of n. So, as per the expression that is shown here, x of n can be recovered from xp of n by removing or deleting or erasing all the other components and retaining the values only over the range 0 to n minus 1. So, from this discussion it is evident that the signal can be that is the time domain signal, okay, time domain signal can be reconstructed from the samples of frequency domain representation. From the frequency domain representation you can obtain. And what is the condition? Is it without any condition? No, there happens to be some condition. Let L be the length of x of n. Okay, let L be the length. For example, if I have say a signal x of n, say 3, 5, 6, 6, 4, right? What is the length? Length is 1, 2, 3, 4, 5. So, there is length is 5. That means the length of the signal is 5 samples over here, right? Similarly, if I consider x of n is equal to 6 minus 2, 3 minus 2, 4 minus 2, 6, correct? So, here length is 1, 2, 3, 4, 5, 6, 7. So, there are 7 samples over here. So, this the condition for obtaining the time domain signal is that the n should be greater than or equal to L. That means, what is n by the way? The n over here indicates the number of samples taken from the Fourier representation. So, I would like to bring back this representation here. You can observe n as shown here, n is the number of samples, right. So, we had considered one cycle only. Why only one cycle? The reason is that this is periodic representation, and first period is same as the second period. All the information that is in the second period is same as in the third period and the fourth period. So, this information goes on and repeats. So, there is no point in sampling the same content again and again. So, you can restrict your samples to only one cycle, that is 0 to 2 pi, and in this region, in this range, how many samples are we considering? We are going to take n, and there is no while talking about this n, I said n number of samples, that may be 100 or 200 or 500, but that n should actually be guided by the number of samples or the length of the x of n. So, x of n is over here. So, x of n, for example, I have shown some 2 examples here, like L is 5 or 7, there's nothing like there is only odd number. So even numbers also you can consider. X of n is equal to say 6 minus 2, 4 and 9. Okay, so this is also, what is the length over here? The length of the signal is 4. So if you are sampling the Fourier transform of this x of n, then n should be greater than or equal to 4. For this example here, if you are sampling and if your intention is to reconstruct the original signal, then the length is already 7, so the signal is already given. So capital N should be greater than or equal to 7. So what are the valid values of N? The number of samples N can be, for example, 8. Sorry, 7, it starts from 7, it can be 8, it can be 9, it can be 25, it can be 30, 40, 50, 60, 100, 200 or even 1000 also. So anything greater than or equal to 7 is a valid option for this n. So with this we are able to conclude that the spectrum of an aperiodic discrete time signal with the finite duration or finite length L can be perfectly reconstructed, perfectly recovered from the samples of x of omega, provided this condition is satisfied, that is n greater than or equal to L. Thank you.